Okay, now we get into the real meat of the calculations in mass analysis. We've worked up to this point on things like molar mass, molecular mass, balancing chemical equations, doing mass-mole conversions. These are all important calculations, and they lead up to this section right here, which is called calculations with balanced chemical equations. So what we're going to do now is we're going to relate the amount of one material, it could be a reactant or a product, to another material. So for example, let's take a look at this example right here actually. So this is the balanced chemical equation right here for the reaction of carbon monoxide, CO, with molecular oxygen, O2, to form carbon dioxide, CO2. Notice it is balanced. Let's check that. There's 2 carbons on the reactant side, 2 carbons on the product side, 2 plus another 2 oxygen atoms on the reactant side, 2 times 2, which is 4 oxygen atoms on the product side. So it's a balanced chemical equation. It looks relatively simple. 2 molecules of carbon monoxide reacting with 1 molecule of oxygen gas to form 2 molecules of carbon dioxide. Now what we want to do is we want to be able to relate quantitatively this relationship between reactants and products. So take a look at a picture here, a diagram, a cartoon of this reaction. It's leaving out a lot of details. The way that this reaction occurs is much more complex than we're leading on to describe it here, but overall this is essentially the change that happens. If we have carbon monoxide and we put it in the same container with oxygen gas, these are both gases. They will collide with each other at really, really high frequencies, like millions of times every second. There'll be collisions occurring all over the container between these materials. Every once in a while, a reaction will occur. And so if we want to make it simple, we could say something like this oxygen molecule pulls off a carbon atom from the carbon monoxide and makes a carbon dioxide molecule. Again, it's more complex than that. There's intermediate steps that occur in this process, but overall that's the effective change. And notice we are wanting to represent this with the balanced equation because we can do numerical calculations with it. It's a more streamlined way of representing this process, but we do want to keep it in mind that when we have an equation like this, we should have a picture in our mind of what that looks like. It doesn't matter what color you imagine carbon or oxygen to be or the size of the atoms at this point, but you should think of this as 2 little balls that are bound together, and that's the carbon monoxide molecule. And if we have a 2 in front of it, that coefficient 2 means that there's 2 of those molecules. Those 2 molecules are reacting with 1 oxygen molecule. The O2 means there's 2 little balls that are attached to each other through what we call a chemical bond. And those 3 molecules, those 3 individual particles, will react to form 2 new particles. So we go from 3 particles to 2 because the product molecules are more complex than the reactant ones. Notice the carbon monoxide has 2 atoms, oxygen has 2 atoms, but the carbon dioxide has 3 atoms. So it's a more complex product than they are reactants. So the stoichiometry is the term we often use. The relationship between these materials, these species we sometimes call them, is that 2 carbon monoxide molecules react with 1. Even though we don't write a 1 there, it's implicit that if there's no number written in front, the coefficient is a 1. So here's effectively what happens. Every time 2 of these react, you get 2 of those. That's what we would call a 2-to-2 ratio. Every time that 1 of these reacts, 2 of those are formed. So this would be called a 1-to-2 ratio, 1-to-2. That allows us mathematically to make predictions about the reaction. If we know how much of the reactants are put into the container, we can predict how much of the products are going to be formed by using these ratios. For example, let's say that 4 carbon monoxide molecules react. So we're not saying we're putting them in the container, we're putting them in the container and they are reacting. 4 of these react. Well, every time 2 of these react, you get 2 of these. So if you put in 4 of these, you should get 4 of those. It's the same ratio. 2-to-2 is the same ratio as 4-to-4. On the other hand, every time 1 of these reacts, you get 2 of the carbon dioxide. So if, let's say, 6 of these react, you would get 12 of these because every time one of these reacts, you get 2. So it'd be 12 as compared to 6. So let's take a look at an example of the type of calculation we could do. And that would be something like the following. Suppose 13 moles of carbon monoxide react. So we're not saying anything about the oxygen, we're just saying 13 moles of carbon monoxide react. How many moles of CO2 are produced how many moles of O2 react? Okay, those are the two questions. So let's take a look. 13 moles of this. Well, every time that 2 of these react, 2 of those are formed. So I'm going to write this in the following. I'm going to take our information that we're given, 13 moles. I'm abbreviating moles as MOL. So that's the number of moles that react. And then I'm going to look at this ratio, 2 moles. So I'm going to multiply it by 2 moles of CO2 divided by 2 moles of CO. We're using dimensional analysis, that topic that we covered way back in chapter 1. Look what happens. Moles of carbon monoxide divided by moles of carbon monoxide is 1. So 13 times 2 divided by 2 is still 13, right? 13 moles, but now we have CO2. And so that answers our question. Every time 13 moles of CO reacts, 13 moles of CO2 react. The reason is, every time 2 of these react, 2 of those are formed. It's a 1-to-1 ratio. What about the oxygen? Well, again, we know it's 13 moles of CO. But now the relationship is 1 mole of O2 reacts for every 2 moles of CO. Okay, 13 times 1 divided by 2, 6.5 moles of O2. Okay, it's as simple as that. We're using these coefficients. They're often referred to as stoichiometric coefficients, but it's perfectly fine just to call them coefficients. We're using those to determine how much of one substance is related to another substance by using these ratios. Now suppose that another question would be, for example, this reaction right here. It's not that different of a reaction, really. It's a little bit different. There's only 3 substances in the first one, but in this one there's 4. 2 reactants and 2 products. So notice this is CH4. We've talked about that in the lecture. This is called methane. It's the primary component of natural gas. Methane has a carbon atom and 4 hydrogen atoms. Reacts with 2 oxygen molecules. There's 2 oxygen molecules, 1 to 2, right? Again, there's no number explicitly written here, but if it helps you, where you don't see a number, you can write a 1. So now, suppose we said the following. 13, I'm just making up numbers here, 13 moles of CO2 are produced. Okay, that's a fact. We're told that information. How many moles of water are produced? Okay, well, it's relatively simple. Every time that 1 carbon dioxide is formed, 2 waters are formed. So we take the information that we're given, and we multiply that by the material that we want is the water. Our question's about water. So 2 moles of water. Divided by 1 mole of CO2. (13 times 2), 26, right? But let's be careful. 26 moles of what? Moles of CO2 divided by moles of CO2 is 1. Moles of water, that's how much. Okay. Now, I'm going to take this one step further. In the previous section, in 3.4, we were looking at mass-mole conversions, mole-mass conversions. We're now going to take that into consideration here. If we form 26 moles of water, or 13 moles of CO2, what we're going to do now is we're going to find the mass of each product in grams. Typically, calculations involving mass and chemical calculations are done in grams. They could be done in kilograms, they could be done in micrograms. Any of the prefixes would be fine. Typically, they're in grams, but it sort of depends on how much material is formed. If you end up with 5,000 grams, it might be more convenient to make it 5 kilograms. If it's 0.005 grams, you might want to write it in as 5 milligrams. Okay, so it depends on the context, but generally, most of the examples you'll see are in grams, less likely kilograms. In a factory setting, it would definitely be kilograms or even megagrams. So let's take a look here. Find the mass of each product in grams. So the way we did that was we said that if we have the molar mass, not the molecular mass, but the molar mass, and I'm going to write down the molar mass for CO2 is 44.01 grams divided by moles. And the molar mass of water is 18.02 grams per mole. Okay? Those are our two molar masses. How did I get those? Well, we looked up in the periodic table the molar mass of carbon, which was 12.01. We looked up in the periodic table the molar mass of oxygen, which was 16.00. There are 2 oxygens, so 16.00 times 2 is 32.00, plus 12.01, you get 44.01. For water, similar idea. Each hydrogen is 1.01, 2 times that would be 2.02, plus 16.00 is 18.02. What this says is that if you have 1 mole of carbon dioxide, exactly 1 mole, that weighs 44.01 grams. If you have exactly 1 mole of water, that would weigh 18.02 grams. And it scales. If we had 2 moles, we would have twice as many grams, 36.04. If we had 2 moles of CO2, we'd have twice the mass, 88.02. Okay? So now let's take a look. Find the mass of each. These are conversion factors. You use molar mass as a conversion factor to go between moles and grams or grams and moles. So if we have 13 moles of CO2, I'm going to multiply that by 44.01 grams per 1 mole. So see how I'm very formally writing out this conversion factor. The mass in grams divided by 1 mole, because that's how much 1 mole weighs. Now, if I had made a mistake and I'd put 1 mole in the numerator and 44.01 grams in the denominator, that would become apparent when you go through the dimensional analysis. Moles divided by moles is 1. We're left with grams. So there we have our answer. So 44.01 times 13 is 572.13 grams. Now you have a criticism here perhaps about significant figures. In fact, there's only 202 significant figures here. It's 13. So in fact, according to the rules of sig figs, we would round this to 2 sig figs. So I will. Significant, significant, not significant grams CO2. We did say that the 0 at the end without a decimal point is ambiguous, so if that really bugs us, we can move the implicit decimal point 2 spots to the left. Left is positive 5.7 times 10 to the 2 grams of CO2. And then in scientific notation, we can write that as explicitly two significant figures. Okay? So the molar mass, we have to become very adept at using the molar mass of a substance to convert between grams and moles. It is one of the most important types of conversions that you'll learn in this course. Practice it as much as you can. Of course, it'll be in the final, but it will also be something that you work with throughout chemistry courses. Now, there's a second part I asked here. I said, find the mass of each product. So we didn't do it for water yet. We know the molar mass of water. We calculated that. We know we have 26 moles of water, so let's figure that out too. So we have 26 moles of water, and the molar mass is 18.02 grams per mole. This is generally something you have to calculate on your own with a periodic table. Sometimes it's given, sometimes it's not. But if it's not, you have to be adept at using the periodic table. The question is, can we convert this to grams? Notice this has grams in it. Notice this has moles, this has moles. The moles are going to have to cancel, and we're going to have to be left with grams. This is the information we have, 26 moles of water, and we're going to convert that into grams. So let me do it the wrong way here. I'm going to show you the wrong way to do it so that you can see. Okay. Moles times moles is moles squared divided by grams. Moles squared per gram. That makes no sense really. Like, what does that mean, moles squared per gram? So that can't be right. So I'm going to cross that out. Let's flip this over. Take the reciprocal. 26 moles of water times 18.02 grams per 1 mole. Now the dimensional analysis helps. Moles, moles, grams are remaining, grams of water. So 26 times 18.02, 468.52 grams. But again, your criticism of my significant figures is valid. I often forget this. 2 sig figs here. So we got to round that off. Most significant, second most significant, the number after it is 5 or greater, so this goes up to a 7. So 470 grams of water. Again, if you consider the ambiguity of having a zero, what's called a trailing zero, without a decimal point, this could be interpreted as 3 sig figs. If we felt uncomfortable, we could move this implicit decimal point 2 places to the left and just leave that. We only need the 0 there as a placeholder, so when we're in scientific notation, we don't need that 0. So it's times 10 to the 2 grams of water, and there we go. Okay. There's our mass of water that's produced from this idea that 13 moles of carbon dioxide are produced. Okay. Now, total mass produced. Products only, right? Produced means products. The first product was CO2, 570 grams. The second one was the water, 470 grams. If we add those together, we get 1,040 grams. Now that one has at least 3 sig figs, so I guess we'd have to round that. It looks like if we put it in scientific notation, 1, 2, 3. Okay, well that's 3 sig figs right there, so we're just going to have to truncate this off. We have to get rid of this, right? 2 sig figs would be 1.0. That'd be the second significant figure, because remember that's a trailing 0 with a decimal point. Trailing zeros with a decimal point are significant. And there you go, 1.0 times 10 to the 3. Now, remember 10 to the 3 is kilo, right? So we could also write this as 1.0 kilogram. We could also convert that into pounds. 1 kilogram is 2.2 approximately. so you would even know how many pounds that is. Of course, that's just for fun there. But the idea would be that this total mass would be around 1,000 grams. 1 times 10 to the 3 is 1,000 grams. So that's the, probably, as I mentioned, one of the most important types of calculations that we learn in this course. It comes at the end on the tail of all of these sort of intermediates, understanding what a chemical formula means, knowing what these molar ratios are, knowing about significant figures in scientific notation. All of that stuff that we did looking at the periodic table builds up to this stuff, and in a pretty rapid amount of time. So what I'm going to do is I'm going to end this right here, and I will have a follow-up video, which I'll call part 2, which will look through one rather lengthy stoichiometry problem from section 3.6, and we'll take a look at that next as a separate video.